Let's start the video lecture. As we know, the physical state of a system is represented in quantum mechanics by elements of a linear space, and these elements are called state vectors. We can represent the state vectors of the Hilbert space in different bases by means of function expansions, and this is analogous to the specifying a Euclidean vector by its components in various coordinates. That means just like we in the Euclidean vector space, we specify the vectors component in various coordinates. We can also represent the vectors in different bases by means of function expansions. The meaning of a vector is independent of the coordinate system chosen to represent its components. Similarly, the state of a macroscopic system has a meaning independent of the basis in which it is expanded. To give the real meaning of this independency on the basis, Dirac introduced a very wonderful notation known as the Dirac notation. He denoted the state vector psi by a new notation called ket and its complex conjugate by psi star by bra, and the scalar product or inner product phi with psi by notation bra phi ket psi. That is, we represent state vector by the ket psi, its complex conjugate psi star by bra psi, and inner product phi with psi by bracket. Further, when a ket or bra is multiplied by a complex number, we get also a ket or bra respectively. In wave mechanics, we deal with the functions psi, r, t, but generally in the quantum mechanics, we deal with the ket vectors, that is ket psi. Like wave functions, kets are elements of the Hilbert space, as I told you earlier. For every ket, there exists a unique bra, and vice versa. The bra vectors are said dual space of the Hilbert space. So the ket represents the system completely, and hence knowing any ket psi means knowing all its amplitudes in all possible representation. There is no reason to single out a particular representation basis such as the representation in the space position. Of course, if we want to know the probability of finding the particle at some position in space, we have to work out the formalism within the coordinate system representation. That is, the state vector of this particle at any time t will be given by a spatial wave function, that is bra r bra r t ket psi is equal to psi r T. In the coordinate representation, further, the scalar product is given by bra-psi ket phi is equal to integration phi star RT into psi RT dqr. That is, there is a also system to represent the the state vector in the coordinate representation, and in any coordinate we can represent the bracket. Similarly, if we are considering the three-dimensional momentum of a particle, the ket will have to be expressed in momentum space. In this case, the state of the particle will be described by psi momentum pt, where p is the momentum of the particle, where p is the momentum of the particle, which can be written as pt psi ket is equal to psi pt. Now we learn about the some important properties of kets, bras, and brackets. Friends, if you like this video, please share this with your friends and subscribe the channel if you are watching for the first time. Friends, in the properties of kets and bras, we will learn one by one. Every ket has a corresponding bra. So first important point is that every ket there exists a bra, that is ket star is equal to bra, or if a ket psi star is equal to a star bra psi, where a is a complex number and there is a one-to-one correspondence between bras and kets. We can also write a ket a psi is equal to a ket psi, and bra a psi is equal to a star bra psi. So brackets, bra and kets also have the properties of the scalar product. Since in quantum mechanics the scalar product is a complex number, the order matters a lot. So we must be careful to distinguish a scalar product from its complex conjugate. So bra psi ket phi is not equal to the bra phi ket psi as bracket phi with psi star is equal to bra psi with ket phi. So we can see that if we change the order of bra and psi, the quantity changes. So the scalar product bra phi with psi complex conjugate is equal to the inner product of phi with psi. We can write in the integral form also. Let's see, bracket phi psi star is equal to integration phi star psi rt psi rt dqr star, which is equal to integration psi star rt phi rt dqr, and that is equal to bracket psi with phi. Note: only bracket psi phi is equal to bracket phi psi happen when ket psi and ket phi are real states. Let us mention some additional properties of the scalar product bra psi ket a1 psi 1 plus a2 psi 2 ket is equal to, you can write bra psi a1 psi 1 ket plus bra psi ket a2 psi 2, which is equal to a1 bracket psi 1 plus a2 bracket psi 2. Next, bracket a1 psi 1 plus a2 psi 2 ket psi is equal to bracket a1 psi 1 psi ket psi plus bracket a2 psi 2 with ket psi is equal to a1 complex conjugate bracket psi 1 psi plus a2 complex conjugate psi 2 psi. Again, brackets a1 phi 1 plus a2 phi 2 bracket b1 psi 1 plus b2 psi 2 ket is equal to bracket a1 phi 1 ket b1 phi 1 psi 1 plus b2 psi 2 plus bracket a2 phi 2 ket b1 psi 1 plus b2 psi 2 ket is equal to a1 star B1 bracket phi1 psi1 plus A1 star B2 bracket phi1 psi2 plus A2 star B1 bracket phi2 ket psi1 plus A2 star B2 bracket phi2 psi2. So these are the properties. Next property is the norm of the bra-ket is real and positive. That is, for any state vector for any state vector ket psi of the Hilbert space H, the norm bracket psi is real, which can be written as psi star psi dqr, and positive, real and positive. Again, norm psi norm psi is equal to 0 only when ket psi itself is 0. And if psi is normalized, then bracket psi is equal to 1 when ket psi is normalized. Next, Schwarz inequality. For any two states, ket psi and ket phi of the Hilbert space, we can show that norm square bracket psi phi is always less than equal to bracket sorry bracket psi and bracket phi with phi. If psi and phi are linearly dependent, that is, ket psi is equal to any alpha ket phi linearly, either psi and ket phi are linearly dependent, where alpha is a scalar, then this relation becomes an equality. So equality only when psi and phi are linearly dependent. Next property is triangle inequality. Also in the Schwarz inequality, analogous to the relation of this is real Euclidean space. You can also write like a vector a dot b mod square is always less than equal to mod of a square into mod of b square. So this is analogous to the state vectors Schwarz inequality. Under triangle inequality, square root bra psi plus phi with ket psi plus phi is always less than equal to square root bracket psi psi plus square root bracket phi phi. Further, if psi and phi are dependent are linearly dependent, then the triangle inequality becomes into inequality. Counterpart of this inequality in Euclidean space is given by in Euclidean space mod of A plus B is always less than equal to mod of A plus mod of B. Now orthogonal states in Dirac notation. So if there are two kets psi and phi and they will be said as orthogonal to each other if they have the scalar product like bracket psi phi equal to 0. So then they will be called as a orthogonal. Next is orthonormal states. Two kets psi and phi are said to be orthonormal if each one of them has a unit norm, that is bracket psi phi is equal to 0 and norm of psi is equal to 1 and norm of phi is equal to 1. Then they are said to be orthonormal states. That means they have to satisfy first the normalization condition and then the orthogonal condition. Physical meaning of the scalar product. So what is the physical meaning of the scalar product? The scalar product can be interpreted in two ways. First, analogous to the scalar product of the ordinary vectors as in the Euclidean space. A dot B, and this represents projection of B on A. The product psi with phi also represents the projection of psi onto phi. That means as in this Euclidean space, the dot product of the two vectors represents the projection of one on the other. In the similar way, In the case of Hilbert space and in Dirac notation, the scalar product bracket phi with psi represents the projection of psi onto the phi. And second, in the case of normalized states, and according to Bohn's probability group interpretation, the quantity bracket psi with phi represents the probability amplitude that system state psi will, after a performing measurement on the system, be found to be in another state. So this quantity bracket psi with phi represents the probability amplitude wherein the state vector psi will be found to be in the another state vector phi when the measurement is done on the ket psi. So friend, in this video lecture we learnt about the Dirac notations, bra-ket and brackets and their important physical properties, and also we learnt about the physical meaning of the scalar product in the sense of Dirac notation, ket and bra. So friends, if you like this video lecture and enjoy the lecture, please press the like button and share with your friends so that they can also learn about these important Dirac notation fundamentals. Friend, these topics comes under B.Sc and M.Sc courses and also used to be asked in the NET CSIR exams. So if you are falling in those categories, so please study these things and share with your friends because sharing is caring, and don't forget to subscribe the Sai Academy channel because we in the video lecture used to bring important physics topics and we discussed through hand written notes in detail. We elaborate the things so that the physics can be learnt in a simple and easy way without any difficulties. Friends, if things are broken in small segments, it will become easy to learn. So please stay tuned in the video and enjoy the learning of physics. Thank you, friends.